In this segment, we'll talk about higher order ordinary differential equations. We'll just talk about a little bit of the background and how we tackle higher order differential equations so that we can use numerical methods to solve them. Differential equations which we solve, they are of this particular form. Whether we are using Euler's method, or we could a second order method, or we could a fourth order method, or any of the methods which we have learned so far. So they are all of the form of the first order ordinary differential equation, and hence we got to figure out that if we have higher order ordinary differential equations like second, third, fourth, fifth order, how do we go about solving them? So let's review when we had a differential equation like this. Let's suppose we had 2 dy by dx plus 3y is equal to 5x, and we were given, let's suppose the initial condition is 0 to be 7. So what we did was, in order to be able to solve by Euler's method or by Runge-Kutta method, we rewrote this differential equation in the form which was needed to be able to do so. So we simply took 3y to the right side divided by 2, and we got y sub 0 equal to 7, and this becomes our function f of x comma y. So let's go and see that how we do that for higher order ordinary differential equations to get a similar format. So when we have a format like this one, here is a second order differential equation, here is a third order differential equation. We cannot simply say that, hey, we can rewrite it as the first order ordinary differential equations as I showed you in the previous slide. So what do we do in this particular case? How do we use the first order ordinary differential equation format to be able to write equations which are of second order, third order, and so on and so forth? So let's go ahead and look at that. So what we're going to do is we're going to go do this through an example. We will take this differential equation which we have here. It's a second order ordinary differential equation, and we'll rewrite it in terms of two simultaneous first order ordinary differential equations so that we can use the methods which we have learned for Euler's method, and then we put a second order method on first order ordinary differential equations to do so. So let's say what we're going to do is we're going to take this dy by dt, and we're going to introduce another variable called, let's suppose, z. So z is an introduced dependent variable, and we are, so I'm going to say. So what that means is that this is not a variable which is there, but we are introducing it. So if we do that, what's going to happen is that this differential equation right here, we can write as 5 dz by dt. Why? Because we can say the second derivative of y with respect to t is now dz by dt. So if that's the case, then we can write 13 instead of dy by dt. We're going to put z plus 17y. We're going to keep it like that, 23 e to the power minus t. And now what we can do is we can say, hey, dz by dt can be rewritten as 23 e to the power minus t. Let's take 13z to the right side. Let's take 17y to the right side and divide by 5. And the question is that, hey, if we are going to rewrite it like this, we got to also have a corresponding initial condition on it. The initial condition will be on z. Common misconception about students that they think that it should be on something else, but it should be on the dependent variable which you have here. So we have to say, what was z sub 0? Z sub 0 is dy by dt at 0, and that is equal to 11. So that becomes our first order ordinary differential equation. However, what we have to think about now is that, hey, we have this differential equation which is given to us, but this is not the one, this is not the only one which we have to solve. We have reduced a second order differential equation to a first order one, but it does not come by itself, because what you're going to see here is that you have z as well as y as the dependent variables introduced. So we should have another differential equation to carry on with this. So rewriting, what we have is now dz by dt is equal to 23 e to the power minus t minus 17y minus 13z divided by 5, and we have the condition that z sub 0 is 11. Now keep in mind, this is now some function, I suppose we call it f1, of not only t, which is the independent variable, but also y and z. And as I mentioned that we have only one differential equation, we need another one, and the other one is nothing but that the dy by dt is equal to z. That is your next differential equation, first order differential equation, and that's also a function of t, y, and z, although y and t are not in the expression right here, but they're still a function of t, y, and z. And this is subject to an initial condition on this variable, the dependent variable y, and that we know that y sub 0 is equal to 7. So what we have is that this is the first order differential equation, and this is the second first order differential equation, and these are now simultaneous. These are simultaneous two first order ODEs, which we can now tackle with Euler's method, or Runge-Kutta second order method, or Runge-Kutta fourth order method to solve. So that is the background of how we take care of higher order differential equations in order to solve them by the numerical methods we know. And that's the end of this segment.